SwayamPrabha. Digital India. Educated India.
Good morning, everyone. Today we will work on solution of Navier-Stokes equations for incompressible flows using simple algorithm. Simple stands for semi-implicit pressure-linked equations. Now I will make a few very important comments here. Simple algorithm was developed during the period late 60s and early 70s at the Imperial College, London. Professor D.B. Spalding was a very well-known professor and researcher at the Imperial College. Also, Professor David Goshman was very well known. Now, in this group of Professor Spalding and Professor Goshman, quite a few very active researchers were working, and among them I can mention about Professor S.V. Patankar, Professor S.P. Bhanka, Professor A.K. Ranchal, Professor Wolfgang Rodi, Professor Micha Wolfstein, and few others. All of them are very famous academicians today all over the world, and they are located at different locations, different places, and they are very visible in thermofluids community. Simple algorithm was primarily developed by Professor S.V. Patankar and Professor D.B. Spalding. Around the same time, another very well-known algorithm was developed. Its name is MAC, M-A-C. It is basically also an acronym. The full name is marker and cell. Now, MAC algorithm was developed at the Los Alamos National Laboratory of the United States, and the scientists who developed are Professor F.H. Harlow, Professor J.E. Welch, Professor Anthony Amsden, Professor B.D. Nichols, and few others. Now, today, many commercial and open source scientific software are available to solve extremely complex problems involving fluid flow, heat transfer, mass transfer, combustion, chemical reactions, etc. Now, in most of such software, wherever flow is incompressible, the basic solver, flow solver that is used is a variant of either simple algorithm or MAC algorithm. That is why MAC and simple, both these algorithms are very important for its relevance and usefulness, and specifically for the learners. These are the pivotal points of learning flows about the flow solvers. So we will discuss about, in this sequence, staggered grid, semi-implicit method for pressure-linked equations, continuity equation, X momentum equation, Y momentum equation, pressure solver, and line-by-line TDMA. Now, equations for incompressible three-dimensional flows are basically continuity equation and momentum equations. In the momentum equations, you can see we have written 1 by Re instead of nu, coefficient of viscosity. That means we have non-dimensionalized the equations. So all the velocities are non-dimensionalized, pressure is non-dimensionalized, and instead of nu, we get 1 by Reynolds number together with the viscous terms. I will mention one feature that is common with both MAC and simple algorithms. Both the algorithms use staggered grid. Now, what is a staggered grid? Let me start with the basic definition of grid topology. A domain is divided by number of cells. We can call it number of control volumes. And in these control volumes, you can see location of u velocity is identified by open circle. Locations of v velocities are identified by this open rectangle. And locations of pressures are identified by this cross mark. So if you take up a cell like this, so these are locations of u velocities. These are locations for v velocities. This is the location for pressure. Now, u velocity here is given by uij. U velocity here is given by ui minus 1j. V velocity here is given by Vij, and V velocity here is given by Vij minus 1, and this is Pij. So Pij, Uij, Vij, you can see they are with the same indices. Uij, Pij, Vij, variables with same indices are staggered with each other. So velocities are located at the center of the cell faces to which they are normal. Velocities are located at the center of the cell faces to which they are normal. And pressure, temperature, etc. are located at the center of the cell. Now, this is two-dimensional grid topology. Extension in 3 dimension is straightforward. Now, there is a reason for choosing staggered grid. If you look at the governing equations, I am going back by one slide. You will see that momentum equations have dp dx, dp dy, dp dz, dp dz. But we do not get any obvious expression for pressure. Pressure is given in terms of pressure gradients. That is for incompressible flows, we know very well. In the case of compressible flow, we get an obvious expression for pressure that comes from the equation of state. But here, that obvious expression for pressure is absent. Instead, we have pressure gradients. So, we require to establish some relationship between the pressure gradient and the velocity. As I said, this location, if this is uij, this is pij, then this point is pi plus 1j. Now, there is a pressure gradient between these 2 points, pi plus 1j, pij. This pressure gradient is directly responsible for this velocity uij. Similarly, in the y direction, this pressure, if this is pij, this pressure is pij plus 1. So there is a gradient between pij plus 1 and pij. And this gradient dp dy is responsible or related or linked to Vij. So pressure gradients in the respective directions are linked to the interfacial velocities. This gives a quicker convergence. So let us now look at the continuity equation. We are considering 2 dimensions. So del u del x plus del v del y equal to 0. So we will integrate this in over the main control volume. That means, the control volume given by this arrangement. This is uij, this is ui minus 1j, this is vij, this is vij minus 1, and this is pij. So we are integrating over a cell volume or cell area, del u del x plus del v del y dx dy, area integral, and we apply Green's theorem for evaluating such area integrals, which becomes line integral of minus v dx plus u dy. And then if we perform the line integral, we will get uij minus ui minus 1j, both at the level of n plus 1 delta y, plus vij minus vij minus 1, both at the level of n plus 1 into delta x equal to 0. We can give a little deeper insight into it, how the integration has been done. This is line integral over the cell of interest. Now you can see u dy. So this dy is positive, uij into dy, ui minus 1j, this dy is in the negative direction. So uij minus ui minus 1j into delta y, both are at the level of n plus 1. Minus v dx. Now vij is defined here, but when you do the cyclic integral, dx is in the negative direction. So vij into dx, it is in the negative direction. So minus vij dx, but that quantity has to be multiplied by minus. So it becomes plus Vij n plus 1. Similarly, in the cyclic integral, this is Vij minus 1 and this is positive direction, in the positive dx. So Vij minus 1 into dx, it is positive, but in the expression for the integration, negative sign is there. So that sign will come, and this will be then Vij minus Vij minus 1 into delta x. Both are at the level n plus 1. So this becomes the discretized continuity equation. That's what we wrote in the previous slide. If you can see, this is equation 5 is the discretized continuity equation. And how this discretization is done, we have shown it. Because of the cyclic integral, we get this form. Now we look at the x momentum equation. As usual, terms have been written: del u del t plus del x of u square plus del y of uv plus del p del x. Del p del x has been moved from right hand side to left hand side, sign has been changed, plus del p del x equal to 1 by re del 2 u del x2 del 2 u del y2. And we perform this integration. Del u del t, we do, this is called mass lumping. We, over the control volume, we do the integration through dx dy, and then over the control volume, this is equivalent to, if you multiply by rho, this will be, in non-dimensional rho is 1, so this is mass by delta t, and uij n plus 1 minus uij at the level of n. The del u del t is taken care of. Now this part of the integration is basically we are doing following way. We are writing it in strong conservative form. So we are moving viscous term to the left hand side. So this becomes then del x u square minus 1 by re del u del x. Similarly, del y uv minus 1 by re del u del y. And then we perform the again integration over the volume, over the control volume, and del p del x is again integrated over dx dy. Now this integration, again, if you apply Green's theorem, we will get something like, minus of this term into dx plus of this term into dy, a term within the bracket, into within the curly bracket, within the second bracket, into dy, del x of this term within curly bracket dx dy. So we will get positive this quantity, which is given by E1 u square minus 1 by re del u del x. That is E1 into dy, and here this quantity minus f1, this we are defining as f1, uv minus 1 by re del u del y. So minus f into f1 into dx, this if we apply Green's theorem, and then we perform the integration. After integration, we are writing e I plus half j minus e1 I minus half j. So E1 at I plus half j minus E1 I minus half j into delta y, and F1 ij plus half minus F1 ij minus half into delta x. That is the result of this integral. Again, this area integral should be converted into line integral using Green's theorem and evaluated. I will do it elaborately in the next slide. And this integration we can write simply p I plus 1j minus pij, simply from this integration, into delta y, both the pressures at the level of n plus 1. Now, how this integration is performed, and this integration is performed on u control volume or on x control volume or x momentum control volume or on u control volume. U control volume means main control volume pressure is at the center. If you recall, when we discussed staggered grid, we mentioned, and u control volume means u is at the center. So u is at the center, that means the right neighbor, immediate right neighbor is pi plus 1j, immediate left neighbor is pi ij. And this is u I plus 1j, this is u I minus 1j. And we perform the integration on this. So as I was mentioning that, this quantity E1, which is u square 1 by Re del u del x, this E1 is defined here and it is being integrated. So E1, which is with respect to uij, its location is I plus half j. So E1 I plus half j into delta y minus E1 I minus half j into delta y. And this is, I told you, this will be f I j plus half. But when we apply Green's theorem, basically this will be minus f1 into dx. Now minus f1, f is defined here, and x into dx, so x is in the negative direction. That makes f into f1 into dx positive. So f1 I j plus half into dx. And as I said, it is minus f dx. So when we integrate this side, this is with positive delta x. So f1 at I j minus half at this location into dx. Dx is positive, but this quantity f1 has a negative sign because of Green's theorem, and that makes it negative, minus f1 I j minus half, this whole quantity into del x. So this is the result of integration of this E1 and F1 along the line integral, along its contour of the defined cell. So it is clear now. That means we get this term we have already explained. These two terms we have now explained, and this pi plus 1j minus pij delta y we have obtained earlier, we have shown in the earlier slide. So now what we will do, we will simply write this term at this point. So E1 I plus half j means E1 has to be written at I plus half j point. That means Uij is defined here, Ui plus 1j is defined here. So mean of that means Uij plus Ui plus 1j by 2 will be U here and its square. So we will get Uij plus Ui plus 1j square, and denominator we will have 4, that is 0.25, 1 by 4, 0.25. Then 1 by r minus 1 by RE del U del x. So basically at this point del U del x means U I plus 1j minus Uij divided by delta x. So Ui plus 1j minus Uij divided by delta x. In the same way, we will define E1 at this point. That means E1 at I minus half j. And that means U square means now it will be Ui minus 1j plus Uij by 2 square. So Ui minus 1j plus Uij square divided by 4.25, and the other term is del U del x, which will be Uij minus Ui minus 1j by delta x. So Uij minus Ui minus 1j by delta x into 1 by I. So that is how, this is basically interpolation of the neighboring cells to find out E1 at I plus half j and E1 at I minus half j. Similarly, F1 has to be defined here. Now when we define F1 here, it is U into V. So U has to be interpolated from neighboring U's. This U is Uij, and U just above this U is Uij plus 1. So U here is, at this point, is Uij plus Ui plus Ij plus 1 by 2. And V is Vij plus Vi plus 1j by 2. So these two multiplications will give it. So Vij plus Vi plus 1j by 2, Uij plus Uij plus 1 by 2. So denominator, it becomes 4.25 into Vij plus Vi plus 1j, Uij plus Uij plus 1. And we also have del U del y at this point. That means Uij plus 1, which is U just above this, Uij plus 1 minus Uij by delta y. So Uij plus 1 minus Uij by delta y. This is how F1 is interpolated at this point. Minus Fij minus up. In the similar way, F1, sorry, not Fij minus up, F1 Ij minus up. So F1 Ij minus up has to be interpolated here. The same way, uij plus uij minus 1 by 2 will give you here, and vij minus 1 plus vi plus 1 j minus 1 give v here. So multiplication of these two terms, you can see vi j minus 1 plus vi plus 1 j minus 1 multiplied by ui j minus 1 plus uij whole divided by 4, which makes 0.25, and we get this term. Similar way, we get 1 by re into del u del y, which will be uij minus uij minus 1 by delta y. So this is uij minus uij minus 1 by delta y. So this is how all these terms are related to E1 at the points E1, as you can see, I plus half j, E1 at I minus half j, F1 at I j plus half, F1 at I j minus half. Those are found out. Now these terms are all we are discretizing at the level n plus 1. So if we write all the terms at n plus 1, then obviously we get quadratic terms here, which are making the equation, or which are basically the definition of nonlinearity. Now we go for linearization. This is local linearization. That means this uij plus ui plus 1j square, we do not write both the terms at the level n plus 1. We write one uij plus ui plus 1j at the level n, another uij plus ui plus 1j at n plus 1th level. So you can see uij plus ui plus 1j at the level n, uij plus ui plus 1j at the level n plus 1. And that is what we do for the next term. And here also for F1 expression, we make vij plus vi plus 1j at the level n multiplier uij plus uij plus 1 at the level n plus 1. So vij plus vi plus 1j, this is at the level n, uij plus uij plus 1, this is at the level n plus 1. We do the similar split between nth level and n plus 1th level for f1 at I minus I j minus half expression also. And all the terms with 1 by re, they are written consistently at the level of n plus 1. All the terms are at the level of n plus 1. And p already we expressed at the level n plus 1, and we are retaining that. So this is how we linearize the equations. And this particular x momentum equation. So what we did, if you look at it little systematically, that this is integrated x momentum equation. Integration, how we got, we have explained, and then we have linearized it. Then we have written the specific expression for E1 I plus half j E1, I minus half j F1, I j plus half F1, I j minus half in terms of the u and u values at the neighboring cells and v values at the neighboring cells. Then we are linearizing it, and then we write the entire x momentum equation. So you can see that if we expand, write term by term, this entire group of terms is basically associated with uijn plus 1, and these are basically grid dimensions, Reynolds number, and u and v values at nth level which are known with uij at n plus 1. So if uij at n plus 1, if this is point of interest, we can call up at n plus 1 point of interest. Instead of ij, if we call it p, then this is basically eastern neighbor, I plus 1j, ij, I plus 1j at the level n plus 1, and this is the basically coefficient of u I plus 1j, and these are also known values, either values of u's or v's at nth level or grid dimensions, geometrical dimensions. Then the western neighbor ui minus 1j at n plus 1. Again, the coefficient is known. These are values at nth level, u or v values at nth level, and grid dimensions. Then northern neighbor ui j plus 1, again at the level of n plus 1, and this is the coefficient associated with the ui j plus 1, ui j minus 1 southern neighbor, and this is the coefficient associated with it. This term is associated with uij at nth level, and everything is known, delta x, delta y, delta t, uij at nth level, and this is basically pi plus 1j minus pij, both are at the level n plus 1 multiplied by delta y. So this is term by term, every term has been written here, and we have expressed it in terms of uij at the level n plus 1, its coefficient, ui plus 1j, its coefficient, ui minus 1j, its coefficient, ui j plus 1 at the level n plus 1, its coefficient, ui j minus 1 at the level n plus 1, and the coefficient. So we can say if this is up, this is ue, eastern neighbor, this is uw, this is u north, this is u south. So point of interest, u at the point of interest uij with the coefficient. If we consider this coefficient associated with uij, then these are the coefficients associated with its eastern neighbor, western neighbor, northern neighbor, and southern neighbor. This term is outside these coefficients of u at and its neighbors at n plus 1 level. This is Uij at nth level plus the pressure gradient term. So we can write, as we said earlier, Uij at n plus 1 and its coefficients. First term is that Uij at the level n plus 1 and all the coefficients. These coefficients, we are saying only this, we are calling this term as delta x, delta y, delta t, but all other terms together we are giving a nomenclature Uij, Aiju. That means the coefficient of Uij that is known as Aiju, coefficient of Uij at the level of n plus 1. So this is this plus delta x, delta y by delta t. Then we will see all these neighbors. This term is gone. So we have accounted for. Then all these neighbors and their coefficients we are writing as summation of UNB is a U at the neighboring points, I plus 1j, I minus 1j, I j plus 1, I j minus 1, east, west, north, south, all are at n plus 1th level and their coefficients. Again, coefficients are called A is a coefficient, A neighbors, coefficients of U. BU is basically this term, delta x, delta y into delta x into delta y by delta t into Uij at nth level plus delta y into pi plus 1j minus pij, both are at the level n plus 1 plus pressure gradient term. In the above equation, this summation of ANB, UNB, all UNBs are at the level of n plus 1, signifies all the convective and diffusive contribution from neighboring nodes. That is, I have already explained, U I plus 1j, U I minus 1j, Ui j plus 1, Ui j minus 1, all are at the level of n plus 1 and their coefficient. The coefficients Aiju and ANBU, that means these coefficients and this coefficient, contain grid sizes and the solution of U and V at the nth level. We have seen that when we have written term by term. The term B equals to minus delta x into delta y into Uij at nth level divided by delta t. That also we have seen. This is basically B. Bn. And in the earlier slide, that means equation 6 has been written term by term so that Aij U, ANBU and BU in equation 7 can be clearly determined. This term, BU term, we will again have a look. This is Uij at the level n multiplied by this. This came from temporal discretization, and so BU equals to minus delta x delta y Uij at the level n divided by delta t. So this is BU, and ANBU and BU in equation 7 can clearly be seen from the previous slide. So this slide gives meaning of this compact form, all the individual terms in this compact form. So this is equation 7 final form of discretized x momentum equation. Again, we have rewritten uij at the level n plus 1 into all neighbors of uij, eastern, western, northern and southern neighbors at n plus 1 time level bu plus delta y into pressure gradient. This is equation 7 that was found through integration of x momentum equation on this control volume defined by dx into dy. This is u control volume on which we performed the x momentum equation to get equation 7. We have already gotten integrated continuity equation, and which was equation 5, and this is equation 7, integrated x momentum equation. We will stop here today, and remaining part of the lecture we will cover on the next day, and we will work with y momentum equation, pressure solver, and the algorithm. Thank you very much. Thank you.